Yeah. Is what?
The moment diagram.
Is Mona correct?
Yeah.
I won't be able to tell you the answer because that's not gonna be fair to everyone. But by just looking at it, it does not look like if your shear is right, then your movement is not going to look like that because it has this portion is positive, right? It has to go up a bit before you jump down.
Oh.
Okay. Any more homework before I start talking? Just a reminder, as soon as I start talking, the homework that turn in after that is going to be considered as a late homework. All right, it's time. Let's get started. Any more homework before I start the lessons? All right. So sort of thing, right? One is today's Monday, so we're going to have our next homework, which is still next Monday, right? And the quiz, we won't have a quiz until next week. So this week is relatively relaxing week, right? And last class we have done with our shear moment diagram. We talk about, we wrap it up with the trapezoidal distributed load, right? And now starting from this class, we're going to jump into a new topics. Now, after we find out all the reaction, all the internal forces of the different member. Now, if we need to check to see if the member is actually breaking under those loading, then we need to move one step forward and look at a stress level. And look at the stress level and see if the stress that created by those external forces, if that is within the material limits or not. Okay. But before we can do that, we need to know what are the stresses of the members. Therefore, and starting from this class, we're going to jump into looking at the different stresses caused by those different loadings. Okay. All right. With that said, I just confirmed that the trip to the National Science Foundation is happening. So with that said, starting from April the 10th, the week of April 10th to the end of April, those 3 weeks, I'll be out. With that said, the classes for those 3 weeks are going to be online. Okay. There might be 1 or 2 classes that I have to host it asynchronously because I might be on the plane during that time. So I won't be able to host a section synchronously. But I will confirm with you once I have more certainty on my flight schedule. But I would expect most of those classes are going to be a synchronized section, but it's going to be online. Yes. I'm going to provide the Zoom links for those different classes. Okay. So for those 2 weeks, we won't have quiz, which is nice. Those quizzes are going to be zoomed after I come back from it. You can send the homework to me to email.
I mean, I think there's a way for Canvas where you can like scan and then you put it in a document and you put it in Canvas.
Would that be easier for you?
Yeah, that would be easy.
Okay, so let me set it up so that we can turn those homeworks in online. Would that work?
Yeah.
All right. Any other questions on this? All right. With that said, let's move forward. Okay. Right, this is what we discussed in the last few classes, is the relationship between your distributed load, the shear, and the moment, right? Now, as we move forward with this topic, no earthquake, right? If something is shaking. Okay. I don't know what's happening, but something is am I the only one hearing that? The shaking? Maybe I need more sleep, okay? Maybe. All right, just make sure it's not earthquake, right? All right, with that said, now with this relationship, we do need to have more practice on this, since there's a lot of integration is needed between the different, you can find the equation for your distributed load, your shear, and moment, right? With that said, I believe the homework problem has some example too. I can release more today and give you more practice on that, right? And again, if you have any question, please reach out to me, and then we can discuss further on that. Okay. All right. With that said, so here is a uniformly distributed load with a simple supported beam, right? We look at this many times. With this particular case, what is the shear diagram look like? First, before we jump there, what are the reactions between a point A and point B? Huh? What is the value? Any clue?
If the value of A would be equal to the value of B, and they would put the B times L over 2.
That's excellent. Exactly. So the reason that we can calculate that fast is because this is a symmetrical structure, right? For symmetrical structure, the two reactions are going to be the same to each other's. Okay? And each of them is equal to your total load divided by 2, because you have 2 support, right? Each hand you're holding half of it. The total load is Q times L. So each of those is going to be QL divided by 2. With that said, what is the shape of the shear diagram look like? Yes. So the straight line is sloping downward. Excellent. How about the moment diagrams? Where is the maximum moment that is going to happen in the beam? In the middle, right? So this is going to be your shear diagrams. The shear is going to start from 0, jump up to QL over 2 because that's the reactions, and they're going to slope down. And at the end of the shear diagram, it's going to be negative QL over L, or QL over 2, and then jumping back to 0. Because this portion and that portion is the same, so this is happening in the middle, right? And the place that where the shear is equal to 0, that is the place that where your moment is maximum. Right, that is the shear moment diagram for these beams, right? If I'm giving you something like this, I expect you to get those answers like this, like in 1 minute, less than 1 minute, right? Because those are the thing that we have gone over many times. So with that said, this is a positive moment, right? So with the positive moment, how would the beam deform? Is it smiling or crying? Like this or like that? It's smiling, right? That is the positive moment means, right? So if your beam is smiling, you know, this has 2 eyes, right? This is my mouth, right? Smiling. With the beam smiling, if you look at the top fibers of the beam, is it in compression or in tension? Compression and tension. Compression, excellent. How about the bottom fiber? It's in tension, right? Excellent. So with that said, let's take a small portion of this guy out. Look at that. And we have the top in compression. We're using the arrow pointing towards the cross section as to denote that is in compressions. And the arrow pointing outward, that is denote the tensions. Now, if you look at the cross section, right, the top fiber is in compression, the bottom fiber is in tension. So there has to be a transition point in between, right? Because your top is in compression, bottom is in tension. There has to be somewhere along the cross section that transition between your compression and tensions, right? Right. If you look at a stress, this is a blow up view of that cross sections. We have a top in compressions, and we have the bottom in tensions, right? And there has to be a point that is in transitions, right? That point is located in the middle for this particular case. In that particular case, we have in particular point, we have no stress. So the top is in compression, and that compression is going to decrease. In the middle becomes 0. And then after that point, it's going to become tension, smaller, getting increase at the end. That is the biggest, right? That is how this stress look like. And just a reminder that you learned from your statics, what is the neutral axis, right? Neutral axis is the axis along which there's no longitudinal stresses or strains, meaning that in that point in the middle, if you connect all the point along the cross section, that is going to create a line, right? And that particular line is called a neutral axis. In that neutral axis, we do not have any stress and we do not have any deformation. That's the strain. Okay. All right. With that said, for the stress, right? Stress is force divided by area. Therefore, it has the units of kip per square foot, pound per square foot, pound per square inches, etc., etc. That is in English units, right? If you look at the SI units, right? That is the kPa, PA, etc. Right? In this class, we're going to look at 2 kinds of stress. One is called a normal stress. And another one is called shear stress. The normal stress is the stress normal to the plane of interest, right? If this is your beam, if this is your cross section, and this cross section is our plane of interest, because we interest in this plane, looking at the stresses on this plane, right? This is a plane of interest. If those stresses is normal, meaning perpendicular to this plane, like what we're showing here, and that is our normal stress. If those stresses are parallel to this plane, and those stresses are the shear stresses, which we're going to talk about next. All right, and that is the plane of interest. It's showing you the plane of interest there. And if that is a shear stress, that is parallel to the plane of interest. And as you can look, if you can see from this graph here, for the normal stress, the maximum is at the edge. In the middle, that is the neutral axis where your stress, your normal stress is 0. However, if you look at the shear stress is 0 at the edge. It keeps increasing, and it's maximum in the middle, and then it's going to decrease again and become 0 at the end. Right? We're going to talk about the shear stress later on. Okay, now, again, our goal here is to find out the stress, right? Now, if I'm giving you the stress of this cross section like this is the stress, for example. We have 3 kip per square foot on top, 3 kip per square foot at the bottom. That is in tension, the top is in compression. We have the middle as 0, right? So for those two stresses, if you look at the equivalent force of those stress, where is that equivalent force going to be located? What? What's that? For the what? Say again. On the right side of the sections. Okay, that's good thinking. So just give you a little hint on that, right? Previously, we talked about triangular distributor, right? If you have a beam like this, you have a triangular distributed load. Where is the equivalent point load? 1/3 from where? From the highest, right? So your equivalent point load like this, right? So if you rotate this 90 degrees, is it similar to that? So where is the equivalent point load? Right, 1/3 here, right? What is its magnitude? Is like Q times L, right? Divided by 2, right? For this guy, we have 3 kip per square foot. The height here is 4. Therefore, the equivalent point load, if we calculate it, is going to be 2 times 3 divided by 2, right? And we're taking 1 foot in and out of the page so that we can calculate the force instead of a stress, right? Right, then we have a top, we have bottom. If we take the moment, and that is the distance because it's 2/3 from the bottom, and we can take the moment at point C. If we take the moment at point C, the moment is created by those two force couple is going to be 3 kips times the distance between those two, right? So that is 3 kips plus 3 kips times 1.33, and that will give you a kip foot. That means if you have a cross section, if you have a moment that is counterclockwise, a kip foot, and that is going to be the stresses that is creating by the moment. Make sense? And if you look at this cross section, those 2 points are going to be the points that we're going to look into because they have the largest stress, right? If anything that's going to break, those 2 points are going to be the most potential points to break because they have the largest stress. All right, this is, if by giving you the stress, we can back calculate what are the moments creating those stress. However, that's not typically what we are interested because in reality, now all the thing that we learned so far is you could first calculate the reaction, right? After you calculate the reaction, that you draw a shear diagram, you draw the moment diagram, right? And that's, you know the moments, but you would like to calculate the stress instead of knowing the stress to calculate the moments, right? So we need to flip that and see, hey, what if I have the moments and I'm interested in knowing the stress, how to calculate that? Okay. Before we go there, I first need to define, give you some definition so that we can talk about this. This is the same cross section, a little bit BC in there. We talk about the neutral axis, right? The neutral axis is the axis where you do not have any stress or strain. Starting from the neutral axis, we have this point of interest, meaning what if I would like to calculate what is the stress at this point, right? This point can be anywhere, okay? And for the point, the distance between the neutral axis to the point of interest is our y. Right, this is first variable I'd like to introduce. And this y has the signs. Go with it. If this y is above your neutral axis, this y is defined as positive. If this y is below your neutral axis, meaning if the point of interest is below your neutral axis, the associated y is going to be negative. Right? Important, right? Because the sign of this y is going to define if you calculate your stress correct or not, because your sign later on is going to represent is a compression or tension. Okay, Mike. And at that particular point of interest, my normal stress is our sigma. Right? It's the second variable. And the maximum normal stress is our sigma max. Right? That is a constant. And the distance between the neutral axis to the edge, that is our c, that is also constant. Right? If I giving you the cross section, the c is going to be null because that's going to be half of your rectangular section's depth, right? Okay, right, with that defined, let's see how we can drive the equation for the normal stress. Let's take that out. If we take those stress out, right, we have the stress at the point of interest at sigma, the maximum at sigma max. Distance between your neutral axis to the point of interest is y. Distance between your neutral axis to the edge is our c. Now, for a similar triangle, the y, because this triangle and a large triangle is similar triangle, because they have the same angle, right? They share the same site. For a similar triangle, the corresponding site ratio is the same, meaning that y over c is equal to your sigma over sigma max. If we move the terms around, we can calculate our sigma is equal to y over c times your sigma max. Now, if you look at this cross section, meaning that this is a cross section, it rotated face to you, right? This is our cross section over there. This is cross sections. And for this cross section, the small area is our dA. The over force of this cross section is integrate the force on that small elements of your cross sections. We do integral, right? And we calculate our sigma. We have an integral is equal to 0 because of equilibriums. We put those in, and here is our equations that we come up with. Again, your sigma max and c are constant. We can take it out from our integral. With that said, we come up with this equation. And the portion that highlighted in red is our first moment of area. For the first moment of area, we saw that before in our statics when we look at the centroid equation. And for centroid equation, the denominator, that is our first moment of area, which is a measure of the distribution of the area of the shape with respect to an axis. Okay. And if you have a irregular shapes, in order to calculate the centroid, we can divide that irregular shape into many, many common shapes, for example, rectangular shapes. And then we can calculate the centroid of that irregular shape through this equation here. So here is an example. This is irregular shape, right? And in this irregular shape, we can divide it into 3 pieces, for example, the first one, the second one, and the third one. The reason that we divide it into a common shape is because, for example, for rectangular shape, we know where the centroid is, right? With that information, then if we can go through this equation basically is saying now the centroid of this irregular shapes is equal to the area of the individual shapes times the centroid of the individual shape divided by the overall summation of the subareas. So using this example to illustrate, now we can divide it into 3 areas, right? A1, A2, and A3. And we can draw a baseline and we define above the baseline is our positive y. And the centroid for each of the subsection is my y1 bar, y2 bar, and y3 bar. And the overall centroid of this cross section is equal to y1 bar times a1, meaning the area of this area 1 times the distance between the centroid to your baseline plus area of a2 times the distance between the centroid of area 2 to my baseline. And that's the same thing for area 3 divided by a1 plus a3, a2 plus a3. And then through this equation, we can calculate for this overall irregular section, where is the centroid in terms of the y directions for this cross section to its baseline. With that said, right, when you calculate your centroid, very important first step is to define your baseline. Without your baseline, you give me an answer, it's impossible for me to judge if that's correct or not. Because if you say, okay, my y bar is 3 inches, right? Is it counting from here? Is it counting from there? Is it counting from there, right? That is not a definite answer, okay? So with that said, calculate centroid, important first step is you need to first define your baseline. Okay. Is it helpful? Because I think in the Slack channel, some of you mentioned that we need to review the centroid moment of inertia a little bit more, because that might be a long time ago. Yes. Why not use this distance? This distance? The reason is always all this calculation has to be starting from the baseline, right? That's why it's important. If you're counting from here to there, it's not counting from the baseline, right? Because you need, that is a distance between your centroid of the sub-area to your baseline. Okay? Good questions. Any other questions on this? Are you good with the centroid calculation? It's going to be important because all those different irregular sections that we're going to see later on in this class, like triangular section, T section, etc., you always need to calculate the centroid first before you can calculate the moment of inertia. That's right. So the rectangular section is going to be your basic sections because you already know where the centroid is. Yeah. Rectangular section and the triangular section. For example, your trapezoidal can be divided into a rectangular and a triangle. And you know that your centroid for rectangle section is in the middle, right? X and Y both in the middle. Right. For the centroid of the triangular section is 1/3 from the larger side, right? Those are the information that you know. Cool. Very good. Any other questions? All right, with that said, after a little review of the centroid, let's move forward. Right, this is our cross section again of the beam. Right, this is neutral axis. We are saying above my neutral axis, my y is positive. Below that is negative. And if we have a small area, that is our dA. And we know that the force is equal to your stress times the area. So we calculate the stress before, right? And if we take the moment from that particular location to the centroid, and here is the integration. And we calculate the stress before, substitute in that, and that is our moments. Again, what we're trying to do is, hey, what if I giving you the moments, we're trying to find the stress, right? We're here one step closer to that. And in this equation, if we look at this highlight area, that is our second moment of inertia, second moment of area, which is also called the moment of inertia. Again, this is a second review for your statics class, right? The moment of inertia is the max property that determines the torque needed for rotating the section. In other words, it is a property to evaluate how hard you'll be able to bend your cross sections depending on your cross sections, right? All right, with that said, now if I'm giving you these cross sections, how many moment of inertia that we have in this cross section about one axis? How many moment of inertia that you think that we're going to have for this cross section? 1, 2, 3. Huh? Infinite, that's great, but why? Huh? There are many points. That is good, but typically for moment of inertia, the moment of inertia is not taking respect to a point. It's taking respect to a line. Because you're trying to bend your cross section through this line, right? For example, if this is my cross section, I'd like to try to bend it, right? It has to be aligned on this cross section I'm trying to bend over with, right? And the answer is right. It's going to be infinite number because we can draw many lines along these cross sections, right? But for a particular purpose, what we interest is the axis passing through the centroid, right? That is the interest of this class. Now, if I'm using the I to denote the moment of inertia, putting in this equation and go through the process again, and here is the equation that we come up with for the normal stress. You don't need to remember all the process that we went through before, but one thing you need to remember is what is the equation for the normal stress of the cross section. Right, your sigma is equal to the negative, make sure that you remember this negative sign here, negative moments of the plane of interest times the y. Again, the y is the distance between your neutral axis to the point of interest, right? Divided by the moment of inertia of the cross section. All right, and that is the equation for the normal stress. One thing I'd like to emphasize again, we have the site for the y. If the point of interest is above your neutral axis, your y is going to be positive. If your point of interest is below your neutral axis, your y is going to be negative. Okay? And for your normal stress, if this normal stress is calculated as positive value at the end, that means your normal stress is in tension. If your normal stress is negative, that means that is in compressions. Okay? That can use as a check for you later on to check to see if your answer is correct or not, which we're going to discuss later on. All right, that is our normal stress. Any questions? Very good. Yes. The neutral axis is the axis passing through the centroid. And for rectangular section, your centroid is in the middle, right? So that's your neutral axis is passing through your centroid, passing in the middle of your rectangular section, right? Great questions. Any other questions? All right. If no questions, let me ask you a question, right? So what is, again, if you look at this equation, right, we need to have the moments at the plane of interest, which we already know how to do. Right? We can draw a moment diagram. We can identify the point of interest in that particular point. We know what is the moment is, right? We know how to do it. As soon as I give you a point along this cross section, then you will know where is the point of interest, right? You know where's the y, right? Another unknown here is your moment of inertia. So here is a question for you. For rectangular section, what is the equation for the moment of inertia? Let me give you an example. Stop sharing. All right, let's see. Let's say this is my cross sections. Now this is my height of the cross section, h. This is the width b. We know the centroid is in the middle, right? Rectangular sections. If we have the coordinates passing through the centroid, this is my x, this is my y. We know how to calculate area. The area is equal to what? It can be, right? That's simple, right? And what is the moment of inertia? First, the question I asked is not correct. I asked you, hey, what is the moment of inertia? Because the moment of inertia, you have infinite ones. So you have to tell me which axis that you're trying to get the moment of inertia, right? So let me rephrase my questions. What is the moment of inertia of this cross section to the x-axis? Moment of inertia of this cross section to the x-axis. It's not a tricky question. Maybe just too long ago when you learned this. All right. Yes, question. Mhm. 0. So again, the moment of inertia is the property of the cross section bending through an axis, right? So meaning it's how hard you need to be in order to bend your cross section along the axis. So for this particular one, it's not a 0, because if that's 0, that means you just cannot bend it, right? Or it doesn't need anything. You just push it and then it'll keep rotating, right? But that's not the case. For the moment inertia for this rectangular section, along the x-axis is 112 bh to the cube. Hope that rang a bell. Right, b is the width, h is the height, right? If you're taking the x-axis, it's always the size that is parallel to your axis times the cubit terms of the height. What about ICY? Meaning, what is that? The moment of inertia if you would like to bend your cross section this way, right? Let me show you. So this is my x-axis. This is my y-axis. ICX is the moment of inertia of the cross section bending over this horizontal axis, meaning that you're trying to bend like this, up and down, right? ICY is the moment of inertia of the cross section bending along this vertical axis, meaning that you're trying to bend it like this, right? With that said, your ICY is going to be 112 h times b to the cube. All right, those are two things that you should be very familiar with, but it seems like we need a little bit of view on this. Is that clear? Okay. So with that said, I'm going to give you a few more cross section as well. So rectangular sections, triangular sections, circle, those are going to be the one that will be used in here. Okay. So for a triangular sections like this, the centroid is located here. Oops. Let's say this is point C, and this is point C. All right, this is Y, this is X, and this is the height, H, and this is the B, and this is the side here. This distance to the edge. This is X. Distance from here. Here is the Y. So the area is 1/2 h times b, right? Based on the height divided by 2. So ICX is 1/36 bh to the cube. ICY is equal to bh squared divided by 72 b minus 2s. Okay. Those for the triangular sections. And we also have the circle ones. guess what? I'm going to upload this equation, this equation for the different sections to Canvas so that you don't need to copy it down. Okay. Okay. All right, so let me focus more on another concept that is important for you to use. How many of you remember the parallel access theorems? Okay, one. All right, let's take a look at it. Can I raise this triangular one? 72, yes. Are we going to post? I'm going to post it on Canvas. Okay. 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 Well, if this is the X, this is the Y, H, E. Okay. In the first example I show you here, we talk about the moment of inertia of this cross section to the axis passing through its centroid, right? ICX, ICY. We call the moment of inertia is always to one axis. What if I would like to take the moment of inertia for the same cross sections, but to an axis passing through its base and the height? Meaning that, what if I would like to know what is the IX, the moment of inertia to this axis, and the moment of inertia to this axis, right? First, I'm going to give you the answer now, and then I'm going to use the parallel access theorem to show it to you how to calculate it. This is going to be 1/3 bh cubed. Iy is equal to 1/3 hp to the cube. Right, the same equation, but just the parameters in front of it is different, right? 12/3, right? Now, here is the parallel access theorem. What's the parallel access theorem saying is the moment of inertia of the cross section to one axis can be calculated as the moment of inertia to its own centroid axis plus the area of the cross section times the d, which is the distance between the centroid to the axis you're taking the moment of inertia square. Okay, and if you have a regular section, you can divide that into a different section and sum those up. Again, please listen to me, right? Don't focus on copying down because I'm going to upload it. All right. Okay, with that said, let's try to use this parallel access theorem to prove, to find the moment of inertia for this one, this case scenario, if I'm giving you this one. Right. Now, the centroid is in the middle. We would like to know what is the moment of inertia of this cross section to an axis at the base of my cross section. Right. This moment of inertia, Ix, can be calculated as the moment of inertia of this cross section to its axis passing to its centroid plus A times D squared. ICI, we already know that that's 112 BH cubed. Area for the cross section is H times B, right? The D is the distance between the centroid of the cross sections to the axis that you're trying to find the moment of inertia with. And this height is equal to what? H over 2, excellent. Because the centroid is in the middle, right? That is H over 2 squared. If you calculate that out, it is 1/3 BH cubed. Right, you can do the same thing for the other axis, which is ICY, this is ICX, plus AD squared. ICY is 112 H times B to the cube, plus H times B times the distance, which is B over 2 squared, and then you get to 1/3 H B to the third. Right, same thing. And that is how you use the parallel axis theorem. Okay. We're going to have more example on this later on when we have a different cross section, because this is the simplest case, right? We only have one of the cross sections. If you have a T section like this, you're going to have multiple subsections. That is where this summation is coming into place. Okay. So that is a brief overview of the moment of inertia as well as the centroid calculations. With that said, and here is the example we would use to demonstrate how this could be done. Right? And here is a simple supported beams with a point load in the middle. And the cross section is a rectangular section with the width of 0.1 meters, height is 0.3 meters. And I'm asking you to calculate what is the maximum normal stress in the beam. Okay. I give you some time to work on it. And then we're going to look at this together. Can I erase this? Good. And this is the equation for the normal stress, since we just introduced it. You might not be able to remember it right now, so I'm going to give it to you. All right, your sigma is negative moment times y divided by I. Right, in order to get this, now we need to first know the moment, right? To get the moment, we need to draw the moment diagram, right? Before we draw the moment diagram, we need to calculate the reaction force, right? Right, that's the whole connection with the knowledge that we learned before. This is going to be 4 meters. 4 meters. And that is 10 kilonewtons. And we are going to have the reaction at 0.8. Y. We have the reaction at point B, By. So what is AY? What is the value for AY? 5 kilonewton, right? Symmetrical structure. We have only 1 point loads. We have 2 support, each of support taking half of it. So it's 5 kilonewtons. So what this 5 kilonewton, what is going to be your shear moment diagram look like? Right? You should be able to draw that in less than 1 minute, right? This is my cross sections. This is 0.1. And this is 0.3. Where is the neutral axis? Let me rephrase my question. Where's the centroid? In the middle. So this is my centroid. And the neutral axis is the axis passing through that centroid, right? This is my neutral axis. And this is 0.15, 0.15. Right, once you have some idea, talk to your neighbors. And get some thoughts on what's the procedures to move forward with. Before you talk to your neighbors, trying to check your shear moment diagrams, because that is the most important first step. That's all. That's right. So first, so two things, right? What we're trying to do here is trying to find the maximum shear stress. Sorry, maximum normal stress. The maximum normal stress is going to happen at the plane, which you have the maximum moment.
Okay.
Right.
Got it.
So you first find the plane that with the maximum moment, that is our plane of interest.
Okay.
On this plane of interest, this is the cross section. We need to find one point that has the maximum normal stress.
Okay. So okay, that's what I was confused about.
Okay,
So it is where the max moment happens.
that's right.
Okay.
Because you think about it, if you this is equation, right? This equation has 3 variables. The moment, your y and I is the same. If you're given cross section, it's not going to change. So you first need to pick the maximum m. You need to pick the maximum y.
And then, so why we're setting the baseline, or I guess the baseline here is the
Initial axis.
traffic, so. why do it?
The y is the distance between your point of interest to your neutral axis, right? So where is your point of interest of that cross section that has the maximum y?
Centrally.
No, the center is 0,
Oh,
right?
no,
Is that right?
Top.
Right?
Okay, yeah, it's 0.0. 0.15. Okay.
And 0.15 is partially right. I'd like to challenge you to think about that. Right, again, I keep reminding you, if you have 5 minutes to solve a problem and your life depends on it, right? You need to take 3 minutes to read through the question carefully and then use the rest of 2 minutes to solve it. Because the worst thing you would like to do is you spend 5 minutes to solve a problem and you found out at the end that you solve a different problem, right? So if you look at this question here, it's very simple, right? Find the maximum normal stress in the beam. The key is the maximum. Where is that maximum located? Right? So if you look at this equation here, this is the equation for your normal stress. The I is going to be the same if your cross section is set. It's a property of your cross section. It won't change. As soon as your cross section is set, the I is the same. So there's two variables here. One is your M, one is your Y. So we first need to find where is the maximum M is located. And where is the maximum Y that will give you the maximum normal stress. Right?
Oh, yeah.
It's right there.
Okay, well, I got.
Johnny, I keep contacting you, right? No, I keep sending you email about, you mentioned about the quest, right?
Yeah, so I couldn't do it today, but I can come in Thursday, get the lab.
Thursday?
Yeah, it's Thursday.
No, it's only Monday. I said it's Monday. But we can talk about it after class, okay? Yeah. It's a room number. Okay. Done? That looks good, but it's partially right. I challenge you to think about it a bit more. Where? So you first identifying where's the maximum moment, right? That is your point of interest. And then you go ahead and identify the y, right? 0.15. But this y, 0.15 is partially right. All right.
0.15 is y, right?
Yes, that could be. Because wherever you go to this line, you go to.
So then, when you're trying to find out X, Y, whatever, you already have to have Y. I feel like there was something like that.
Figure out.
I didn't figure out what you're talking. 0.15,
So
or would it be like 0.149?
no, 0.15 is right, but it's partially right because there's more point than the 0.15.
Points?
There's more points.
for the
Meaning-
entire line.
Now, there's the entire line on the top, right? This 0.15, that means you're choosing a point for the entire top line,
Oh, so it's
right?
triangle that goes out.
Not really. So let's say this is your baseline. The neutral axis is your baseline.
Mhm.
So you told me that the maximum y is 0.15,
Oh, so
right?
it's max y, so it's the corner, right? Yeah, this area is, so this is the baseline. This is 0.15, so we're trying to find this.
No. So can you borrow pens?
Mhm.
So this is the baseline, a neutral axis.
Mhm.
You can find any point along this line.
Yep.
And any point along this line, the y is the distance between this point to that point.
Mhm.
It's a straight distance. So this is your 0.15, right?
Mhm.
But it's also point that on the bottom that also give you this 0.15, right?
Mhm.
But that's negative. So those points are also, you think about it, give you the maximum stress too,
So it could be,
positive or negative.
okay,
Because the positive, that means that is in compression, right?
and yeah, so it's just, you're finding just both sides of it.
That's right.
Okay.
Yeah. All right, giving an interest of time. Let's take a look at this together, okay? So now you should be very familiar with how to draw this shear moment diagram for now, right? Shear is in kilonewtons, moment is in kilonewton meter. You start from 0, and because the AY equal to 5, you jump up 5, right? 5, have a straight line. Because the 10 kilonewton going downward, you drop down 10, that's -5. Go straight again at the ends. You go back up to 0 because the By is equal to 5, right? And that is your shear diagrams. Your moment diagram basically just calculating the area for this guy here. This is 5 times 4, this is 20, right? This is 20. That is your moment diagram. Straightforward, right? Now, because we are trying to find the maximum normal stress. The first step is, if you look at the whole thing, the whole beam here, which planes give us the maximum moments? Where? It's this guy here, right? Meaning if this is the beam, the middle of the beam, this cross section here, has the maximum normal stress, right? So that is our plane of interest. So the first step is to find the plane of interest where the maximum moment is located. First step. Now, we found, oh, in the middle of the plane, middle of the beam has the maximum moment. Let's chop it out, right? Chop it out and then look at the plane. This is the plane in the middle. Which point along these cross sections is going to give us the maximum y? That is our point of interest. Which point along this cross section has the maximum y? This is my cross sections. Half the point 0.3. So that's step one, step back, right? The y is the distance between your neutral axis to the point of interest, right? So we have a limited number of points along these cross sections. Which point has the maximum y? Yes. The tallest point, right? This point? Everyone agree? How about this point? How about this point? So any point along this line that has the maximum y, which is equal to 0.15, right? Is that all though? So let's calculate it. So this is negative 20 kilonewton meters. The y is 0.15 meters. What is the moment of inertia for the cross sections? What is the equation again? 112 bhq, right? So 112 b is 0.1 meters. Cube h is 0.3 meter to the cube. And that will give us 0.000225 meter to the fourth, right? So that is 0.000225 meter to the fourth. If you calculate it, it's going to be 1333.33 kilonewtons meters square. This is negative. But this, yes. Is that right? Anyone has the calculators? Let me double check. All right. All right. So this is the answer, the normal stress, right? It is negative. We said if that's positive, that's in tension, right? Negative, that is in compressions. So this negative means in compressions. So if you think about, if this is a beam, have a point loads, you have a positive moments, the top fiber is in compression, right? The answer is in compression. That give you some confidence that your answers, the site of the answer is right. That is one way to check it. But this answer is partially right. The reason is, if you look at these cross sections, in addition to the point on top, which is give you the maximum y, what about the point at the bottom? Are they giving you the same distance? It's also 0.15, right? So the point at the bottom here is also going to give you the maximum normal stress. However, those y, what is the y at those points? Negative 0.15. If you substitute in this equation, it's going to be negative 20 kilonewtons meters times negative 0.15 meters divided by 0.000225 meter to the fourth. That will give you positive value. What is that positive value means? Tension, excellent. So that means for this cross section, with this loading, both the top fiber and the bottom fiber are going to have the maximum normal stress. The top is going to be in compression normal stress. The bottom fiber is going to have the same normal stress, but is in tension, right? So for a problem like this, it's going to be, this is going to be positive, positive minus, right? Because it could be the point on the top and also could be the point at the bottom. Questions? Yes. That's right. Unless I ask you, hey, what is the maximum compressive stress? What's the maximum tensile stress? Then you need to give me the corresponding one. Right? All right, with that said, your homework's going to be online. I'll see you on Wednesday.